The ideas I showed you in 10.3, these kinds of facts are really important. Being able to take the problem and factor it completely, and then knowing that two identical square roots multiplied together is the thing inside because of what it means to be a square root. It's a number you can multiply by itself to get 5, and we're busy multiplying it by itself so we get 5. That's at the heart of this entire chapter. And so as we're doing problems in 10.4, know that I will be using that a lot. There's more than one way to do these problems. There's at least 5 or 6 good ways to do most of them, but I'm going to do almost all of them with this idea. And my students have had really good success when they buy into this method and just start doing it. They end up liking chapter 10 because they can do it. Just like the square root of a product is the product of the square roots, the square root of a division or a fraction is equal to the fraction of the separate roots. You can break apart a division or a multiplication. Now 64 can be thought of a lot of ways, but one of them is this way. And the square root of x squared can be thought of as the square root of x times x. Now, this is a 2, this is a 2, this is a 2, this is an x, and we have 8 over x, and we're done. When you get really good at this, and some of you may get really good at it, you'll just start to see that there's an 8 coming in top and an x coming on the bottom, and you'll just get the strong feeling that this is correct. I'd still advise you to do quite a bit of this unless it becomes just impossible and you know what the answer is and you're 100% sure. I would expect you still to be doing this work, most of you. Again, if you go to tutors, they'll show you good stuff, but it won't always be the stuff that I think's best or easiest. One way to do this problem is to use the fact that the quotient of two roots is the same thing as the root of the quotient. So you could rewrite this problem this way. And now that that's just a regular 26 over 13, you could do 26 divided by 13, and it's 2, and so you get the cube root of 2, and you're done. That cube root looks a little sad, so let's make it look marginally better. And this is the time-honored way to do this. I like this. Everybody likes it. You probably like it as long as you can remember to do it. But I would like to point out that the thing I've been drumming on forever here is pretty good too. If you break apart the 26 up here, it is 2 times 13. So this cube root of 26 is the same thing as the cube root of 2 times the cube root of 13. And so we could write, instead of the cube root of 26, we could write the cube root of 2 times the cube root of 13. These would cancel, and we'd have the cube root of 2. And that's not that bad. It has the advantage of getting really, really good at figuring out what these parts are and how to make these parts work. So I recommend thinking about it. In some problems, you're asked to rationalize the denominator of a fraction. That means doing something to the fraction so that you get an equal fraction, where the denominator is a regular number like 11 or 12 or 13, no fractions or decimals. Well, here the denominator is not a regular number, it has a square root in it. So what we're going to do is we're going to look at the denominator and ask ourselves, what needs to happen in order to get rid of all the square roots? Well, we've got one of these, and what's the key fact about the square root of 2? The key fact is if you multiply it by itself, you get 2. That's the key fact, the key idea in all of these sections in chapter 10. So what we want to do is multiply the bottom by the square root of 2. That's what we need. What we do to the bottom, we have to do to the top, otherwise we won't have an equal fraction. So in the bottom, we're getting 7 times 2. In the top, we're getting 3 times, and these are leftover pieces, so we put 2 times 5 or 10 inside the square root. and the 7 times the 2 is the 14, and we're done. Notice you can't cancel a number inside a root with a number outside a root ever. So don't try to cancel the 10 and the 14. If they were both inside a square root, you could do it. If they were both outside a square root, like the 3 and the 14, you could do it. But one inside, one outside, you can't do it. So we're done. Let's try another one of those because it was so much fun. If you go to a tutor, depending on who you go to, you might get somebody who says, well, the thing to do is multiply top and bottom by the square root of 12 because this square root of 12 will match this one. And while that is somewhat okay and it works fairly well, I think doing the prime factorization of 12 is best. Takes a little bit of work, but look what happens. That square root of 12 can be written this way, and now what kind of pieces do we need? We don't need 12. We don't even need any 2's because those 2's fit together nicely. What we really need is one more root of 3. That's what we need. So this method of analyzing what these numbers are built out of helps you be very effective and efficient and accurate. Now on the bottom, what do we have? We've got 5 times a regular 2 times a regular 3. That's 10 times 3, that's 30, and we're done. There's no canceling. 3x and the 40 don't cancel. So we're going to break apart all the pieces. I'm going to take the square root of the top and the square root of the bottom and then break apart the square root of the top. 40 is 8 times 5. 8 is 2 times 2 times 2. So we've got the prime factorization here. So I'm going to break apart the 40 into the 2 times the 2 times the 2 times the 5. Now we're trying to rationalize the denominator. That's the goal in these problems, to make the denominator be a root-free number. So we analyze what we got. We got a couple of these. That's going to make a regular 2. But we need one more to match this and one more to match this. So we're going to have to multiply the bottom by a square root of 2 and a square root of 5. So we're going to have to multiply the top by a square root of 2 and a square root of 5. So now what do we have on top? We have a 3 times a 2 times a 5 times an x, all in one leftover container. And on the bottom we got a 2 times a 2 times a 5. So here on the top we have a 30x inside the square root sign, and on the bottom we have a 20. Done.